Hey yo! Welcome. 11.5, the last video of the book, y'all. Straight up. So first and first, mostly, this is gonna be pretty complex. However, if you need to watch it multiple times, y'all, um, do whatever you need to make it work. Or you might just watch it through the first time and be like, simpatico. I think that doesn't mean what I wanted it to. Anyway, what we're doing today is limits of summations and a very classic problem, the area problem, which is a problem that you're going to look at a lot in calculus. There's a lot of different ways to do it. We're looking at just one today, and really only one this year. You look at others and even more um, accurate ways of doing it next year. Anywho, let's jump right in. So first of all, we need like a little skill before we can really look at the area problem, and that skill is looking at the limit of a summation. Okay. Now, if you kind of just focus yourself on this portion right here, this should look familiar from chapter 8, where you looked at the actual, summation from 1 to infinity of a geometric sequence. Alright, so when we saw this summation of a geometric sequence, we had like from 1 to a number, and we were able to use a specific formula to actually compute what the summation would be, and that's this right down here. If you can remember that, it's a sub 1 times 1 minus r raised to the n over 1 minus r. That should look familiar. If it doesn't, we need to kind of just brush up on that slightly. But this is, what we're using now. The only variation we're going to do to this is say, well, if I'm, in limits looking for as n approaches infinity, how does that affect this formula? Well, the only n in this formula is this exponent right here. And, r values, when they're between 0 and 1, they're fractions. So if we have a fraction raised to an exponent, and that exponent is getting bigger and bigger and bigger and bigger and bigger, that fraction is getting smaller and smaller and smaller and smaller. So this is going to an approaching 0. That's the only thing that's really changing in this formula. So therefore, this r raised to the n is almost negligible. If as n approaches infinity, this becomes closer and closer to nothing, we can kind of just ignore it. All right, so the formula that we're going to be looking at is simply a sub 1 over 1 minus r, which would be the limit of that geometric sequence in summation. Now, there's a lot of other formulas like this, where we say, if I'm looking for the summation of a specific type of equation, I can come to this formula and kind of substitute it. And we're not going to go through how they all come to be, but this page, and you have this in your book as well, I think it's page 789, shows you, a couple of those, and the most common. So if you have the summation of a constant, well, it's just going to be the constant times, whatever your ending value is. If you have the summation of I squared, or the summation of I, the summation of I cubed, so all these different things which we will see being used as we go through examples. So why don't I just jump to the next example, and we can actually see I think 2 of them in use. Alright, so the first one is just a matter of saying, okay, I have the summation of I from 1 to 200, so it's basically the summation of 1, then I becomes 2, 2, I becomes 3, 3, I becomes 4, 4, so 1, 2, 3, 4, all the way up to 200. Add them all together, what do you get? Right, so I have the summation of I. Let me go back and see what that should be able to convert to. It should convert to n times n plus 1 over 2. That should be my formula for computing that. So if I come back here, that's exactly what I'm going to do. Right? So I use that formula and I say, okay, n is 200, that's my ending value, my upper limit. 200 times 200 plus 1 over 2. I evaluate 20,100. So first example, always super easy, and then it becomes deathly difficult. So let's head on to deathly difficult. Obviously, this next one is far more complicated, but it's not going to be too ridiculous if we break it down very, very small steps and just take it piece by piece. Like, don't jump down here and say, oh my god, I have no idea what happened. Just look at the first piece and just follow along with me. So we have the summation from 1 to n. So n isn't actually defined in this one. We know that n is going to be some constant number, but I just don't know what that number is yet. Okay, so as these i's change, the I is variable, the n is still going to be a constant number. So even though it's a variable in the equation, we have to remember that n is a constant. Okay, that's going to be very, very important. So first off, just like in the last one, I would say, what do I have that I can substitute? Do I have anything where I know the formula of it and I can use it? Well, no. If I went back to that other page, I would see I know the summation for I know the summation for I squared, I know the summation for I cubed, but none of those things are actually right here, unless I was to actually square this binomial like this says to. So why don't I do that first, and then maybe I'll have some things that I can substitute in. So down here, the first step was just rewriting, and the next step is what happens when I do square this binomial. Now, it might not seem very apparent that this becomes this, so why don't I kind of write that out. 1 plus I over n times 1 plus I over n. Now when you multiply the first, obviously 1 times 1 is 1. Multiply the outside and the inside, you're going to end up with 2i over n, positive. And when you multiply the last ones, you get I squared over n squared. Now my issue here is I don't want a whole bunch of things over different denominators. I want everything under one denominator. So the common denominator between all three of these things, in order for me to add the fractions, is going to be n squared. So this one's fine, I can keep that one. This one I have to multiply by n. So this one stays the way it is. The middle one I have to multiply both the top and the bottom by n. So this becomes 2ni over n squared. And the first one, the 1, technically 1 over 1, I have to multiply both the top and bottom by n squared. So that becomes n squared over n squared. Now you can see how these three fractions, if combined into one, translate to this one term right here. The 1 over n stays. So that goes there. This becomes this. Alright, now the next step is simply a matter of saying I still don't want two different things on this side. I want one. Okay, so I'll multiply them. Well, 1 on the top times this, well, that stays the same. N times n squared gets me over n cubed, right? But I'm still not too fond of having a constant in the denominator. If I can, much like if you think back to the last section, if you have something that's dividing on one side, or something that's multiplying the entire thing on one side, that's a constant, you can kind of take it out of the summation and you put it on the other side. So this divided by n cubed here becomes this 1 over n cubed on the outside. Okay, so that's where that fraction on the outside comes from. Over here, when you multiply, you get n cubed, and you just take that constant out. Remembering is very important. Remember that n is a constant in this case. Okay, so once we have that settled, I can now take each of those three terms that was left here. I had n squared, 2ni, and I squared. Let's highlight those. N squared, 2ni, I'll put in a different color. And lastly, I squared. Those are my three terms of the polynomial on the right side. I'm going to take each summation separately, and remembering again from the previous sections that I can do that. then it makes it a lot simpler for me, because now look, I have the summation of I squared. I can deal with that. I have the summation of 2n, which is a constant, times I. The summation of I can deal with that. And the summation of n squared. N squared is a constant, so I can deal with that. Okay? So now let's run back and see how this somehow turns into this long mess. Well, this is the summation of a constant. If I look back the previous slides again, or if I look at page 789, I can see that the summation of a constant will just be that constant times the n value. Well, n squared times n is n cubed. Okay? Now, with the second one, I have the 2n, which is a constant, times I. Well, the summation of I is going to be n times n plus 1 over 2. So this is 2n I, right there, the summation of 2n I. And the last part is I squared, and this whole long mess at the end here simply is our formula for the summation of I squared. Right? Now it's simply a matter of mushing all of this together. Right? And once we combine all the like terms and push this all together, our final piece is right here. Now, what is this? I mean, we just went through all of this work, and I have no idea what I even did. This formula right here is a function of n that is going to tell me the summation from 1 to some number. It's a function that represents every summation of the original equation given here. Okay? So they aren't the exact same thing, this and this new function, but this new function is going to tell me all of the solutions of the previous. So if I wanted, say, the summation of the original function to 200, I could put in an n value of 200 and I could get that summation. If I wanted of the original function right here from 1 to 30, I could come to this formula and say, put in a 30, what do I get? That's my summation. Now, what's also really cool about this is that we're going to be looking at how does it affect, how is the function affected when I take those n values and I look at the limit as they approach infinity. Alright, so with this new function I can actually find the limit, and in effect I'm finding the limit of a summation. Okay? So now that it's in what's called rational form, I take the limit as n approaches infinity, which, if you remember, again, pulling back from the previous sections, when I have the leading coefficient of the top and bottom being the same, the limit as n approaches infinity is basically just going to be 14 over 6, which simplifies to 7 over 3. Okay, the last part, finding the limit, is actually probably the easiest portion of doing a problem like this. Alright, so let's see. If we could try out two things, exercise 5, which should be a simpler one, just a matter of using some of those properties and substituting, and then also trying exercise, let's say 15, all of it. Exercise 15. There's different parts. There's I think A, B, and C. So let's try all of those. Alrighty. And now, finally, since we've gone through kind of like the nitty-gritty skills type stuff, we can look at the area problem. Okay. Now, what is the area problem? I think I've said it a couple times. Basically, what it is you're looking at a function, a non-negative function, and you want to find out what is the area underneath this curve. Okay, the area underneath the curve is going to be bounded in 3 different places, well, 4 places. And by bounded, I mean, restricted. It's going to be restricted by the function, so it's going to be below the function. It's going to be restricted by the x-axis, so above the x-axis. And then I also have to put in some vertical lines, x equals a and x equals b. Between all 4 of those places is where this function is going to be restricted. Not the function, where the area is going to be restricted. What this turns out to be is actually very, very fascinating that something so kind of like crazy as the area underneath the curve can provide us such important information. The most common application that is generally given in schools are things like velocity, acceleration, and placement. When you talk about physics, all three of those things are related in this way, where the area underneath one curve is actually the function of one of those others. And their relationships are very, very interesting. We'll get into that kind of stuff later, or maybe even next year when you're in calculus. I mean, you definitely will. I'm not sure if we'll cover it this year. But let's just focus on actually how we find the area under the curve before we start talking about its applications and all that good stuff. Okay, so when we have a simpler figure, square, circle, trapezoid, we have a formula for it. We have a way of saying, okay, I know it's base times height, I know it's 1/2 base times height. But this is different. We're bounding it by a function. So things are going to get a little bit strange. And one of the most common ideas for trying to compute the area underneath the curve is to break it up into rectangles. Okay, so not take the entire figure as it is, as one kind of misshapen piece, but to break it into smaller and smaller pieces. And this is where the idea of the limit comes in, because I don't want these big pieces in here and then I end up losing out on these pink areas that I'm not actually taking the area of. I want all of these rectangles to approach being as small as they can be. If they are so minuscule that they are right next to each other, there is such a minimal amount of empty space that I'm not accounting for, that the area underneath this curve is a very, very, very close approximation of what it actually should be. So that's where the idea of limit comes in, making these rectangles as close to 0 wide as possible. Right? So let's look at this example and then see how that works out. We're looking at a function, 6 minus x squared, and I'm going to bound it at x equals 0, so that's my a. X equals a will be right here. I'm also going to bound it at 2, so I just want right here as well. So what I'm going to do is try and basically do a base times height type formula, but I'm going to have to adjust it. Okay? So the base on this is obviously, because it's bounded from 0 to 2, it'll be 2. But I'm going to break it into 5 different rectangles. 1, 2, 3, 4, and 5. So each width, if I'm breaking 2 into 5 different parts, each width should be 2/5. So that's where I'm going to start with this one. So the first one goes from 0 to 2/5. The next one goes from 2/5 to 4/5. The next one goes 4/5 to 6/5, 6/5 to 8/5, and 8/5 to 10/5. And that brings me all the way from 0 to 2, the whole region that I'm trying to get the area of. And what we want to notice here, and what's going to be very important, is that this value right here, the first y value, is exactly two multiples less than this one. This y value is 2 multiples more than this one. This y value is 2/5 more than this one, and this y value is 2/5 more than this one. So depending on which rectangle I'm looking at, either the first, the second, the third, the fourth, or the fifth rectangle, each one can be defined by just saying 2/5 times whatever rectangle I'm looking at. So if I wanted, the coordinate for the fourth rectangle, I could say 2/5 times 4, I'd get 8/5. That's where my rectangle is. If I wanted the area for the third rectangle, I could say 2/5 times 3, 6/5. Right, so that's going to be important in how I define the height of the value. Right? So when I look at just the area of a specific rectangle, I need width times height. And width, we know for all of these different pieces, is 2/5. Right? The height for all of these things is just going to be the function value at that point, right? If I go back to the previous section, if I want the height at 2/5, I need f of 2/5. If I want the height at 4/5, I need f of 4/5. If I want the height at 6/5, I want f of 6/5. So hopefully that idea makes sense there. So we have the width being 2/5, the height being f of that value. And this is where that 2/5 times whatever rectangle we're looking at comes into play. Okay, because I need a way of expressing every single rectangle without explicitly showing it every single time. I need a function that will define it. So I can say f of 2i over 5, where I is whatever rectangle I'm looking at. Am I looking at the first one, the second one, the third one, the fourth one? So I want the summation of all of these areas from the first rectangle to the fifth rectangle. Okay, and now we can use the information and the skills that we were just using to try and solve this. All right, so first of all, let's get rid of this idea of a function inside of the summation. My function is actually 6 minus x squared. If you remember that from the previous slide, 6 minus x squared. So I'm going to actually put that in here. Instead of f of 2i over 5, I'm going to put 6 minus 2i over 5 squared, because my function. I'm inputting 2i over 5 for x. And now I can start to evaluate it and simplify a little bit. I'm going to put the constant out in front. Let's flip back so you can see that again. I have a constant being multiplied here, so this is going to come out in front of the summation. And then I also am going to have two different summations happening inside of one, so I can split those up. So that's what happens here. The constant comes out in front, and I take each summation separately. Now again, we need to think back and say, okay, the summation of a constant is going to be that number times the n value, so this is 30. And over here, I have the summation of I squared. Okay, so what am I supposed to be doing with that I squared? Well, I squared is, the formula for that is going to be n times n plus 1. If we look back again, 2n plus 1 over 6. So when I substitute n in there, it's 5. It's 5 times 6 times 11. I'll have 6 and 6 on the top, so those will go away. So 5 times 11 is going to give me 55. 55 times 4 over 25. That gives me my 44 over 5. So now I just have numbers. I can deal with numbers. 30 minus 44 over 5 times 2 over 5 gets me 212 over 25, which approximates to 8.48. So I can say my approximation for the area underneath this curve, or in other words, my approximation for the sum of each of these 5 rectangles is 8.48 units. Alright, and that's what I've effectively done. Now, in the next example, we are going to take this a step further and take the limit of the summation. So I don't want to just be looking at this and say I'm going to split it into 5 rectangles and that's it. I want to say I'm going to split it into an infinite amount of rectangles, so much so that I have such a negligible amount of red space here that my approximation is going to be super, super accurate. Okay, so let's look at the next one. The area of the region bounded by the graph of x squared between 0 and 1. Okay, so I have going from here to here, bounded by the function and the x-axis. Got it. Okay, now things are getting a little bit technical here based upon the formula. And again, you can see the formula. I kind of skipped over it here because I didn't want to confuse you too much. 793 is where the formula is. And we'll try and explain it piece by piece as we go through. The width of the rectangles is going to be b minus a over n. Now, why? Well, b minus a is basically how you're going to get any specific width, right? I'm lucky on this one because a is 0, b is 1, so I could just say that the width of the entire thing is 1, and I could easily figure that out. but let's say instead I was bounded by 0.25 and 0.36. Well, the only way you're going to figure out that width is if you do 0.36 minus 0.25, which is essentially what this is saying, b minus a. So that's saying that's the width of the entire figure, and the n on the bottom is the amount of rectangles you're going to split it into. Okay? So right now I'm keeping n kind of variable. It is going to be a constant number. That's going to approach infinity, in fact. But right now, I don't know how much I want to split this one unit into. I know that I want to split it into n rectangles. So that's the width. And the height, again, just like we talked about before, is going to have to be a function of the width. So, if I'm looking for the height here, I need to look at f of this point. If I'm looking for the height here, I need to look at f of this point. If I'm looking for the height here, I need f of this point. So that's why this is a function value. And the b minus a comes directly from up here. It's the same idea. Over n, again, because of the width of the rectangle. And a plus that value. Well, that comes from, again, this idea of I'm lucky that it's from 0 to 1 here, but if I started at 0.25, and let's say that I was looking for my first value, which was n units over from the starting point, I need to say 0.25 plus so many units will be giving me my first rectangle. I can't just say so many units away is my first rectangle, because that might come out to be 0.1, and that's not actually within the bounded region that I was looking for. So I need to make sure that all of these little rectangles, all these little pieces that I'm finding, are inside of the actual bounded region that I'm looking for. Okay, so this is our formula for height. And I go and I plug in values, my 0 for a, and my 1s for b, and what I get is f of I over n, which my function here is x squared. So when I do f of I over n, I get I squared, n squared. Alright, so at this point, I've thought about a lot, my brain is fried, but all I've really done is found out the width of one of my rectangles and the height of one of my rectangles. I have not done the summation of all the rectangles. I have not even done the limit of all of the summation of all the rectangles. So I still have a lot of work to do. So my next step is actually to take the summation of height times base. So let's go ahead and do that. The summation of what I found the height to be and what I found the base to be of my rectangles. When I multiply them together, I get I squared on the top and n cubed on the bottom. Again, some of you hopefully are right on with this one, whereas this is a constant, so I can take it and put it out in front, 1 over n cubed. And on the inside, all I'm left with is I squared. I squared is coming up a lot, so hopefully at this point you can recognize this is the formula that we use to evaluate the summation of I squared. Okay, so I just put it in there, and then I can bring the 1 over n cubed back in. And that's simply just a matter of multiplying the denominators. So what I have now, right here, is a function where I can put in some value of n and say I'm going to split this area right here into 1,000 rectangles. What is my approximation for the area underneath the curve? And I'll get some number. But that's not really good enough. I don't want to split it into 1,000 rectangles. What I want to do is to find the limit as the number of rectangles approaches infinity. I want that to be so minuscule that it's a negligible amount of space that I'm missing. So I take the limit as n approaches infinity. I have the same degree leading variable on both the top and the bottom. So my limit is simply 2 over 6, which is 1/3. And we are done. Okay, I know that feels like a lot. Without my explanation, it really doesn't take as long. But I have pretty long-winded explanations in there. Hopefully they were helpful, and if not, we'll review it again. Um, but the good news is that we're going to try exercise 33 from 11.5, and then boom, chika, what, you're done. 11.5 is done. We might discuss a few other things in class, but you got no more videos to watch. Your year is almost up. Congratulations, woot woot, and what all the young kids are saying these days. All right, have a fantastic night, and I'll see you guys in class.